Let's get started on material for exam 6 in your textbook, chapter 17. We're going to look at what makes reactions spontaneous. What do we mean by spontaneous? We've studied up to this point reactions in terms of their energy requirements and their energy output. And this particular diagram, it should be familiar to you. Reaction progress is on the x-axis, energy of all the components, everything in the reaction, the energy is on the y-axis. So in this case, the reactants start at a higher energy than the products have, which means it's exothermic. The energy has to go somewhere. We have to conserve energy. So if the reactants are higher in energy than the products, then we have to give that energy up, and that makes it exothermic. But also, we can look at this diagram in terms of what parts of the diagram address kinetics, or the rates of reaction, and those that address equilibrium. If we look at just the central part of that diagram, the hump in the middle, that the difference between the reactants and the top of that hump, maybe I better draw it up here so I can talk with my hands. But if we have energy here and we have progress here, and we start off with reactants there, and we end up with products here. And this distance between here and here is the activation to energy. And that part of the diagram here and here is speaks to the issue of kinetics. How fast does the reaction go? The bigger this difference between reactants and this activated complex, the bigger that difference, the slower the reaction. So it's got to get over that hump. Then if we look at just the beginning and the end, we don't care how it got there, we're talking about equilibrium. Okay, that's just a review so that we can talk about why these things happen, because we can't always explain why a reaction occurs. I got the word already, painting the road. We can't always explain a reaction, the progress of a reaction in terms of these two concepts. Sometimes we need some other explanation, and that's where we're headed today. Okay. Right. As a reminder, well, actually, this is not a reminder. This is new stuff. The kinetics of reaction depend upon the path. What sequence of elementary steps do we go through to get to the products? So this is an overall picture of the reaction, and you could have several steps going on in here. And these steps depend on whether or not you have a catalyst also. Because what a catalyst does is, if you remember what a catalyst does, it gives you an alternate pathway at lower energy. So that's why kinetics is a path function. In other words, it does depend on the path that's taken for the reaction. Whereas thermodynamics is a state function. It doesn't care how it got from here to here. All it needs to know is the beginning and the end. And that can come in handy when we're trying to assess the energy requirements or the energy output from a reaction. We don't need to know this part. We just need to know the beginning and the end. Okay, what's a spontaneous process? Well, this is one of those terms in chemistry that is fairly consistent even in common vernacular. Spontaneous just means it happens on its own. It doesn't need any input from the outside. Thermodynamics will allow us to predict the direction of the reaction, but it doesn't tell us anything about the speed. And in terms of whether or not the reaction will go, if we say the reaction is spontaneous, that means we don't have to do anything. It will go. Now, it doesn't say how fast it'll go. It just says it will go. Like, I think I've used this, I hope I've used this illustration before. Diamond is thermodynamically unstable. I mean, it will go from regular oriented tetrahedral structure to individual carbon atoms over time. It'll just take millions of years to get there. Okay, so let's take this as an example. Try to identify the problem in predicting spontaneity, whether a reaction will go or not. Say we have 2.4 moles of gas in a 4-liter bulb. Okay, so we've got a 4-liter bulb here, right? 4-liter volume, and we've got 2.4 moles of gas in here. Right? And it's connected, and the temperature is 32 degrees, and that's constant. We don't have to worry about the temperature changing. And it's connected to another bulb that's 20 liters. Okay, by way of a valve intervening, and this one is 20 liters. And this is in a vacuum. Okay, so what do we expect to happen when the valve opens? It's not a trick question. When you open that valve, you should expect the gas to go until it equalizes. Right? It has the same pressure throughout. Right? All right, how do we explain that? There's no energy change, right? Because the temperature stayed the same. Right? So that's just one of the many problems that are presented for spontaneous processes that we can't explain with either kinetics or thermodynamics. Well, actually, we are going to explain thermodynamically, but we have to introduce another concept to get there. And this is what scientists and engineers were working with in the early part of the 19th century when steam engines were coming online. They were trying to figure out, how do we make steam engines more efficient? Well, they needed more information and they needed to shift their paradigm to accommodate the new technology. Right, and that's what we're going to do now. But we need some terms first, obviously. We should already know what delta H is, right? We've been introduced to that before with thermochemistry. Delta H is enthalpy. And enthalpy is like a potential. How much potential energy can you get from a process, or do you have to put into a process? Exothermic versus endothermic. And then there's another concept called internal energy. And internal energy of any system is the total amount of energy accounted for by anything you can think of. We usually divide that into kinetic energy and potential energy. We'll talk about those in a minute. So this is internal energy. I gave you the system surroundings lecture yet? I don't think so. Okay. So when we're talking about movement, energy movement, and the concept that's coming up that I haven't named yet, we have a defined system, and it can be in terms of volume, be in terms of components that are involved in the system, and then everything else is surroundings. And the reason we're doing this is so that we have this barrier between the two, and we can talk about transfer across that barrier. Okay. So I think I've got a slide on this, but I'm going to go with it. If we talk about energy, and this is the term we use for heat transfer. This is simply heat flow. And there's a difference between this one and that one. They're related, yes, but there's a difference, a significant difference. This is actually measured. This heat flow is measured using conditions of the systems and surroundings and their relative temperatures. You don't get heat flow unless there's a difference in temperature. And then I might as well do the last one. This term is work. And have either one of you had physics or physical science? Okay. In physics, the term work is very strictly defined as a force acting through a distance. So force times distance equals work. So if I were to say, stand up here and push on this wall, I'm applying a force to the wall, right? But it's not moving. So I'm not doing any work. But we still have to conserve energy. So where'd the energy go? If I push on this, I'm expending energy. Where did it go? I didn't do any work, so it had to be converted into heat. I'm raising the temperature of my hand and the wall. Not by very much, but it is measurable. So these terms are central to the discussion that's coming up. Back to this one, system and surroundings. So if heat is leaving the system, then we say that's exothermic, right? And it has to have a sign, right? A number, a unit of measure, and a sign. The sign here is going to be negative because everything is referenced in terms of the system. Something is leaving the system, it's negative. So vice versa, that would be positive if it were endothermic. And these are transferred across this barrier between the system and the surroundings. Now, as a practical matter, the surroundings would be the rest of the universe. That's a little hard to grasp because we really don't know how far the universe goes. So what we generally do is we isolate. Okay. Now the barrier here and here can be spoken of in terms of three possibilities. If it's open, if this barrier is open, that means that both mass, matter, and energy can transfer across that barrier. If it's closed, the restriction is only to the mass. So energy can transfer across that barrier if the system is closed. And if the system is isolated, then neither mass nor energy can transfer across that system. Now, that's not very useful except in terms of calorimetry. We did the calorimetry lab. We had an isolated system in our cups, our styrofoam cups. Okay, and this isolated system surroundings is in terms of this barrier. This one is always isolated because we want to talk about what's in the surroundings and what's in the system. We want to be able to quantify them, so we need to know exactly how big that surroundings would be. Okay, so there's our terminology. Internal energy can be subdivided into kinetic energy and potential energy. And enthalpy, I'll get to that one in just a minute. Also, internal energy is equal to Q plus W. Internal energy can be defined in terms of heat flow into or out of the system. This is a change, right, delta? Or work done on the system or work done by the system. Okay, so those two terms also are equal to internal energy. Okay, now go back to our model. I'm not going to redraw it with our bulbs. One bulb's got some gas in it. The other bulb, well, actually, it's a different one because, no, it's the same one. 4-liter bulb has gas in it. 20-liter bulb is a vacuum. So what are these terms? Delta H. Delta H and Q both require a change in temperature. And if the temperature is 32 degrees Celsius and it doesn't change, that means that this is 0 and this is 0. Okay. How about work? Is work being done on the system? Well, the gas is expanding against no resistance at all. There's no force being applied. So no matter how far it moves, it's not doing any work either, right? So there's no work being done. And then internal energy being the combination of Q and W, both 0, internal energy is 0 also, right? So all 4 of those terms are 0. All right, that presents a problem because if there's no change there in any one of those terms, how do we explain the spontaneity of the process? It's going to occur, right? But we can't explain it with these terms. We need another term. And that's what they came up with in the middle of the 19th century to explain what was happening. All right. Oh, there's explanations in subsequent parts. Okay. Okay, here's our new term, entropy. So, all right, let's see, we've defined, put our terms over here that we've defined. Delta H, delta E, Q, and W. Now we're going to add another one, entropy. Entropy is a concept that was derived primarily from a mathematical approach to these thermodynamic questions. It was introduced by Rudolf Clausius in the middle of at the end of the Civil War. Only he was in Europe, so he didn't have to deal with all the carnage. What did he mean? He's got that typical stare that photographs had in those days. I think they did that because the time required for an exposure was fairly long, up to a couple of minutes. So you just kind of had a blank stare. Anyway, this concept is, we're going to introduce it in terms of an easily understood description. And then we're going to actually give you the reality. All right, first of all, notice with these two flasks, like we had, one has gas in it, and the other one's a vacuum. When we open it, they expand out. Notice any difference? The density has decreased, right? You've got more space between the particles. And that concept we generally refer to as disorder. In other words, the molecules have more space. So that we've increased their entropy by making them more disordered. We find that if we if we push the same number of molecules into a smaller volume, we have to introduce more order to them. They don't have as much room to move around. It's like the difference between a clean room and a messy room. My sister's rooms, as I was growing up, they were usually fairly ordered. Right? My room and my brother's room were a mess. So we had more entropy than they did. So these terms, notice that we usually don't define these variables in absolute terms. In other words, we may call this entropy, but as far as measuring it goes, we usually measure differences in entropy. Right? What's the change of entropy from this position to this position? Just like enthalpy is the same way. And internal energy would be the same way. That delta gives us a difference. So if we see a delta S being positive, that's an increase in disorder. Let's see, I'm trying to associate the signs with our system and surroundings here. Let me get this out of the way. It's kind of making it a little too busy. So if we say the system is increasing in disorder, well, we would have to change, with our example, in order to make the system more disorderly, we'd have to increase its volume, wouldn't we? If we wanted to decrease the disorder, we decrease the volume. That's one example. We're going to talk about another possibility in terms of the energy input also in just a minute. But for the terms, if the term is greater than 0, then we increase disorder, and less than 0, we increase disorder with positive and decrease disorder with negative. Yeah, that's an understatement. This concept of disorder is useful for your first introduction to entropy, but it's very, very, very oversimplified explanation for entropy. In reality, what we're talking about, entropy as a thermodynamic function, is the number of possible arrangements. We call those microstates. How many possible arrangements of particles can you get? Say if you have the same number of particles in this volume versus this volume, say we have 1 mole of gas, right? The number of possible positions that they can occupy increases with greater volume. So that gives them 1 microstate. Say we only have 4 particles. Let's keep it simple. So if we have 4 particles in each one, we could have particle A here, B here, C here, and D there. Then we could also have an A over here and a C over there. We could have several possibilities, right? Microstates. But if we do this, we could have an A here, a B here, a C here, and a D here. But they wouldn't have to just swap places. We could have a C there, or we could have a B over here, or we could have a D over here, right? The number of possible microstates increases with volume. So that increases this entropy. This value here is greater than this value here as far as entropy goes, because of the number of possible arrangements that can be theorized for a given number of particles in those 2 spaces, those 2 volumes. So if we're trying to understand spontaneous processes, and this includes both physical and chemical processes, the processes tend to be spontaneous when the number of microstates or possible arrangements increases. So we're going from our example from a confined 2.4 moles into from 4 liters up to 20 liters, was it? In other words, going from a small space to a large space, we're increasing the entropy. And anytime you get delta S positive, that means spontaneous. Now, it may be accompanied with energy change, like energy input or energy release, but if this is true, that process is going to be spontaneous. It will happen without any intervention. Okay, here's my ABC molecules. And what we're trying to do is simplify the concept of microstates. And the arrangements of our particles are going to be most probable. I think at the end of the first semester, we talked about quantum mechanics. And it was all probability based. Right? That tends to be the way we have to go in physics and chemistry, because we can't see everything that's happening at the microscopic level. So we approach probabilistically. And in this case, the most probable arrangement of particles is that's given by the largest number of possible microstates. Okay. So if A, B, and C are on one side of those two bulbs, there's only one possibility. They're all on one side. If we put one on the other side, then you can have 4 possible microstates. If we put 2 on either side, then you can have 6. Or if you go and put 3 on one side and 1 on the side that they left, then you're back to 4, and then 1 if you put them all on one side. So the most probable arrangement is that third, the middle one. That's what we would expect in terms of their microstates. Okay. Entropy we can discuss entropy in 2 different ways. Now, I don't think your book goes into this much detail, but I think it's important for you to understand the difference between positional entropy, which is what we've been discussing up to this point. Positional entropy simply refers to where are they at any one instant. Positional entropy. And if we look at it in those terms, then we see that any material, let's keep it simple, any element that is a solid has fewer possible microstates. In other words, fewer possible arrangements, because all the molecules are locked in position. Right? They can vibrate a little bit, which gives them some options in terms of entropy, but not many. Then if we add some energy and we get them to the liquid state, then they have more possibilities because they can slide past one another. And if we turn them into a gas, then the possible microstates goes through the roof. So we have an increase in entropy from solid to liquid to gas, based solely upon their positions, possible positions, arrangements in the space that we're given. Another possibility is in terms of the energy that's contained. And these are kind of like they're first cousins, because we know in order to go from solid to liquid to gas, we've got to put energy into it. So let's see. If we look at it in terms of the process being either exothermic or endothermic, and here we've got an exothermic process, here we have an endothermic process. and we look in terms of what's happening to the system. We'll talk about the surroundings also in just a minute. But in terms of the system, if we put energy into the system, we're increasing its energy entropy. And we can also reason that in terms of if we put energy into that system, the molecules in there are going to be moving faster. So at any one point, any one span of time, they can occupy many more positions because they've got more energy to get from one place to the other. An endothermic process decreases the entropy. So going this way, we're decreasing the system entropy, but okay, now for the surroundings, what are we doing to the surroundings, right? If we move energy into the surroundings, now we're increasing the entropy for the surroundings and vice versa. Okay, so we'll come back to that in just a minute. Let's look at it in terms of, let's see if we have a rudimentary grasp of the concept with these possibilities. What would be the sign for the entropy for each of the following? And we want to focus on the system. So if alcohol is evaporating, right, where is it getting its energy? We know it's going to become a gas. But in order to do that, it needs energy input. So it gets its energy from the surroundings, right? So that would be what type of process? It would be an endothermic process to evaporate, okay? But in terms of delta S, what would that be? We're going from a liquid to a gas, we would increase the entropy, right? You don't have to memorize that. That's just for general knowledge. There are equations that are associated with calculations of entropy. And this Boltzmann equation, entropy equals some constant times the natural log of W, which is the number of possible microstates. So as usual, these equations they mean something to people that are studying that concept. But as far as we're concerned, we need something that's more useful, right? And we're going there. Okay, so the evaporation of alcohol then would be positive delta S. How about freezing of water? If we go from a liquid to a solid, we're decreasing the entropy. Right? Number of randomness is decreasing for freezing water. If we compress an ideal gas at constant temperature, we're moving the same number of molecules into a smaller space. They have fewer possible microstates available. We're also decreasing the entropy. Now, that would not be a spontaneous process, would it? No, you'd have to put energy in and force it to that point. Heating an ideal gas at constant pressure. Constant pressure means the volume's increasing, isn't it? Right? So we're increasing the entropy. We're increasing the positional entropy. We're also adding the energy to the system. So we're can reason it in terms of energy entropy also. So the energy input will also increase the entropy. So you can think of it in either of the two terms. If we dissolve sodium chloride in water, we're taking that solid sodium chloride, and we're moving those ions further apart. They're giving them more possible microstates available. So we're increasing the entropy of the sodium chloride. Okay. All right. Laws of thermodynamics. Laws of thermodynamics. The first law is the change in energy for the universe is equal to zero. In other words, the amount of energy that the universe had at the beginning is the same amount that it has now. That's the first law of thermodynamics. We're focusing on the second law of thermodynamics here. And the second law says that delta S for the universe and I do mean the universe, the entire universe, is always positive. So in other words, the universe is occupying more space. Edwin Hubble showed that with redshift on distant galaxies. We know that the universe is expanding, so it's expanding with the same amount of material into a larger space, so the entropy has to be increasing. And the third law, let's see. I'm going to leave it at there because I don't want to throw you off. We don't need to know the third law right now. So in any spontaneous process, there's always an increase in entropy of the universe. Now, terminology. If we say the entropy of the universe, we're talking about everything. But we have isolated our system and surroundings. So it's possible with this situation for the delta S to decrease. Okay, because we've isolated it from the rest of the universe. So when your textbook says delta S for the universe, sometimes they're actually meaning delta S total, right? Which means the sum of the delta S for the system and the surroundings. That's what they're saying when they say universe. So delta S for the system plus the delta S for the surroundings equals the delta S total, which is in our isolated arrangement here. Okay, so I added that note in there just to be sure I didn't miss that point. Okay, there's the first law. Energy is constant for the entire universe, but the entropy is increasing. Right, and there's our first equation. Let's see. Let's put it over here. Delta S total equals delta S system. Oops. Need big S first. Plus delta S surroundings. Okay. So what we're saying is, and when we say, and the universe there, I think, I think I modified it. There we go. That's what we actually mean. When they say universe equals system plus surroundings, and that's true for the universe. But in this case, delta S is always going to be positive. But for the bottom one, total, it can be negative. And that's what we're looking for to determine if a reaction is spontaneous. What is the sign of the delta S? Is it positive or is it negative? Let's see. If delta S is 0, right, we're at equilibrium. In other words, the process stops where it is. Now, we know in terms of physical and chemical processes, if we have an equilibrium situation, then we've still got action right at the microscopic level. Right? For instance, saturated sodium chloride solution. You've got salt in the bottom of that solution, and you're getting dissolution of the solid, and you're getting precipitation at equal rates. That's equilibrium. But in terms of delta S, we're not changing the total delta S for the system surroundings. That's equilibrium. Okay. All right. Say we have this process. We have any substance, which is designated by capital A, is a liquid. And we're saying the process is going from liquid to solid or solid to liquid. So which direction involves an increase in energy randomness and which one is positional randomness? Well, in order to go from a solid to a liquid, you have to add energy. Right? So from right to left, is an increase in energy randomness. Positional randomness, well, it should also be the same if we're going from a solid to a liquid. From left to right, we have an exothermic process, right? If when you go from liquid to solid, it's got to give up energy because there's kinetic energy of the liquid molecules. And when you fix them into position, then they're not moving as much. So they got to give up that energy. So that's an exothermic process from liquid to solid. Energy randomness favors the formation of the solid, decreasing from liquid to solid. Okay. It's easy to get confused because I get confused sometimes with this concept. In terms of energy, if we can give up energy and go from a liquid to solid, the energy randomness favors the solid because it's an exothermic process. In other words, we're going from a higher energy state to a lower energy state. And in the past, we've identified that as a preferred process. In other words, the products at lower energy are happier, right? If we can anthropomorphize it, because they're more stable. Stability favors energy. So if energy randomness, if we go from a liquid to a solid, then our decrease in energy randomness is favored based upon what we know of exothermic reactions, right? Nitroglycerin, right? Look at it cross-eyed and it'll explode, right? What does it do? It produces products with much, much lower energy, right? Nitrogen gas, oxygen gas, let's see, what else is in there? Carbon dioxide, water. Those are more stable forms. So we know that that one is a spontaneous reaction. All it needs is just a little kick. So the energy exothermic process favors the reaction going from liquid to solid. Positional randomness decreases from liquid to solid, reducing the number of microstates. So its preferred direction is from right to left, from solid to liquid, if we're talking about positional randomness only. So we have to look at the balance between the two in order to determine the final outcome. So in these possible scenarios, as the temperature increases or decreases, which takes precedence? As temperature increases, positional randomness dominates. Increase the temperature, then we're saying that we're increasing the number of microstates. We're putting energy in the, we're giving the molecules more energy so they can move from one place to the other quicker and introduce more possible microstates as a consequence. So as temperature increases, we get positional randomness dominates. Now, there's also a difference between whether you're already at high temperature or you're starting at low temperature. At high temperature, positional randomness dominates as a release of energy becomes less important. In other words, it's kind of like, let's use an analogy. At high temperature, it's like a millionaire, right? Somebody that's got several $1,000s in their pocket. Right? And I'm going to be a generous benefactor, and I'm going to give them $10. Right? Do they care? No. Right? That's influence is much less significant at for somebody that's rich than it is for somebody that's poor. So the high temperature is the rich person. Positional randomness dominates because energy, the money exchange, is less important. Whereas at low temperature, if we get down to lower temperatures, then say I've only got $10 in my pocket. Somebody comes along and gives me 10 more bucks. That's 100% increase in my available cash. So that's at low temperature. So in that case, that money exchange, that energy exchange, the energy randomness is favored, and positional randomness becomes less important. So at what temperature is there a balance between energy and positional randomness? For our previous scenario from solid and liquid, where you have solid and liquid, the temperature at the melting point, that's where we get a balance between energy and positional randomness. And you're not going to see a change in temperature at all. If you've got solid and liquid together, at that temperature, it'll stay at that temperature until you either get all solid or all liquid. All right. These, I don't know why I keep these slides in here because they're such difficult concepts. It's hard to teach them. But I'm going to try. Describe the following as spontaneous, non-spontaneous, or you can't tell. Okay. Maybe we don't have enough information. Okay, an exothermic reaction that becomes more positionally random. Positional randomness favors spontaneity, right? Exothermic also, in terms of energy randomness, exothermic favors the right. So I would say this is a spontaneous process. Both driving forces are favorable. How about exothermic and less positionally random? Well, the exothermic favors the forward direction of the reaction, but the positional randomness being less is opposing that. So we can't tell because we don't know which one is larger. And if we also say endothermic reaction and more positionally random, those are opposing forces also, so we can't tell with those. Endothermic is not favorable, positional is favorable. So what we need here in order to answer the question is magnitude. Which one's bigger? And then endothermic and less positionally random, that is non-spontaneous. Those are both unfavorable processes. We can also say that the first one and the last one are not affected by temperature. I'm not so sure about that. Let's hold that concept in reserve. Or can we reason it out? If they're not affected by temperature, based upon our previous slide, that would mean that we have to be at high temperature. So I'm not sure about that one. Let's hold on that concept till we get a little more information under our belts. Right. We're going to talk about free energy in a few minutes. And that's a better and more useful concept for determining spontaneous reaction versus a simple discussion of entropy. Now, everything's based upon that discussion, that entropy concept, but free energy takes us to the next level that makes it more useful in determining the spontaneity of a reaction. Okay. So the delta S of the surroundings depends upon the direction of heat flow. Right? If we're talking about energy entropy, of course. So as if heat leaves the system, we're adding energy to the surroundings. And we're also increasing the randomness in general for this process. So that exothermic process says that delta S for the surroundings is increasing for an exothermic process. Whereas if heat enters the system, it's just the opposite. Okay. So the magnitude of delta S for the surroundings depends upon the temperature. It's directly proportional to the temperature change. If we're talking about the surroundings only, then the delta S for the surroundings is directly proportional to the temperature. The change in entropy for the surroundings is much greater. There's a much greater effect if we start at lower entropy. It's like the dollar exchange. We start at lower entropy, then any entropy change that we introduce is percentage-wise magnified. So what we're saying is that this delta S is directly proportional to the heat transferred. Okay, I can see where confusion is setting in already. We're trying to relate the change in entropy for the surroundings in terms of the heat flow and the temperature. So this delta S is more significant as the temperature decreases. In other words, they're inversely proportional. I misstated earlier. In terms of heat, yes, this is proportional. Let's see. This means proportional. Proportional to the heat that enters or leaves the surroundings. It's inversely proportional to the temperature, because as the temperature decreases, we get a smaller term in the denominator, which increases the delta S. So at lower temperatures, the delta S is more significant. The change in delta S is more significant. So we're saying that for the surroundings, the delta S is directly proportional to the heat entering or leaving the system, but inversely proportional to the temperature relative to its starting position. All right. So the magnitude of the entropy change, which is delta S, is proportional to the heat and temperature. And if we're going to quantify this will be in joules. This will be in K units. Kelvin degrees, but well, I can't say degrees because Kelvin doesn't have degrees. So what that means is, if for an exothermic process, we're adding heat to the surroundings, right, increasing this term, and even if the temperature is constant, then the delta S would be positive. And if heat's going the other direction, then this term would be negative. All right. So here's the, let's see, delta H now, in this case, is going to be proportional, excuse me, no, I'm sorry. Delta S for the surroundings is equal to enthalpy divided by temperature, but we've got a problem. Because if delta H if it's exothermic and negative, then this needs to increase in size. So if delta H is negative, then the more delta H you get, the smaller the value, the more negative. So we got to put a fudge factor in. That's why the negative. simply because of the choices we made earlier in terms of signs relative to the system. Okay? So we have to have that negative in there in order to make these things mesh. All right. Now I went from Q to delta H, and we need an explanation. Delta H and Q are not necessarily equal to one another. They use similar units of measure, joules. Delta H would be joules per mole, something like that. Q is simply joules. So under what conditions are they equal? We need to know that because we can measure Q, but delta H is not measurable unless certain conditions are met. Right? These are different values. Delta H is enthalpy, Q is heat. Think of enthalpy in terms of thermodynamic potential, much like internal energy. It's the potential of the system to either release heat or absorb heat. And it's defined by this equation. Right? Delta H equals total internal energy plus any change in pressure times volume. Right? So that's our starting point. Now we're going to do some algebra. If we have an equivalence for delta E, which is what? Q plus W, right? So if we substitute delta E in here, we have Q plus W plus any change in pressure and volume. That's enthalpy. Now we have an equation where we've got both terms, delta H and Q in there. Now we need to find out when would those two be equal to one another. Well, obviously, they would be equal when the rest of it goes to zero, right? If we can make that one and that one both go to zero, or that combination go to zero, then we've got delta H and Q equal to one another. Right? I'm speaking algebraically now. Okay, so under what conditions? Well, let's suppose we have constant pressure. If we have constant pressure, then it's no longer part of the delta term. We bring the P outside, and now it's only P delta V. So at constant pressure, we have P delta V. All right. What is work? Well, work, did we do this discussion when we talked about thermochemistry? That would have been last semester. What we determined was that W equals minus P delta V. Work, and this is for a gas, minus P delta V. That's work in any system. I think we must have done it last semester. But we came up with this expression. That's equal to work. So if we substitute that one for W, then we have if W equals minus P delta V. So now we've got plus P delta V, and then W equals minus P delta V. Those terms go to zero. So what that means is that delta H enthalpy equals, change in enthalpy equals heat transfer under one condition, when the pressure in the system is constant. If you can keep the pressure constant, then you can measure a Q value, a movement of heat into or out of the system, and equate that to the enthalpy. All right. We must have done that last semester. So the takeaway is just they're only equal when pressure is constant. After all that yammering, we got one concept out of it. Okay. So believe it or not, the change in entropy for the system and the change in entropy for the surrounding don't have to be exactly the opposite of one another. If we're moving stuff into and out of the system, it doesn't always mean that the entropy changes are equal. But we can say, since we know this needs to be positive for spontaneous reaction. So if we can say that both of these are positive, and that can be in terms of positional or energy entropy, whichever one gives it a positive value, both are positive, then we know that the process is spontaneous. If both of them are negative, then we know that the process is not spontaneous in the forward direction. But in the reverse direction, it is spontaneous. Okay? Now, the only way to determine whether it's spontaneous if they have opposite signs, if delta S is positive here and negative there, then this change has to be larger than that change in order to give us a positive value here, and vice versa. So in those cases, we have to know what those actual values are in order to predict spontaneity using this concept. Okay, Josiah Willard Gibbs. He was an American working at the late to the end of the 19th century. And he was interested in what part of the energy, in other words, if we have an exothermic process, right, like this, and this right here is our delta H. Right? He wanted to know, because everybody knew at that time that this was a theoretical difference. Right? You could measure it, of course, but it's theoretical, and there was always a loss. He wanted to know how much of that could be used to do work. He called it free energy. In other words, the energy that was free to do work, how much of that was free energy? And we gave it the symbol in his honor, G. Now, the concept of free energy was being used by a number of different scientists. And you have formulas that go along with their free energies that are different than the one that Gibbs used. But Gibbs is the most commonly referred free energy formula. Right? And this was his deduction, mathematical expression for free energy. In other words, this amount of energy is available to do work, and it's based upon the total enthalpy, the potential energy, heat energy, minus temperature times change in entropy. Okay? So this is the amount that's being lost from this term to give you the available energy for doing work. Delta H minus T delta S. And of course, that T has to be in Kelvin units. All right, so we do a little algebra here. If we divide the whole thing through by T, everything through by T. So that gives us, and we actually would do it minus T, because we're going to get rid of that minus sign. So that gives us minus delta G over T equals minus delta H over T, and this is plus delta S. Okay. So next, let's see. Oh, this term right here. Delta S for the, if delta S equals, let's see, where are we going next? Okay. This term right here is found here, right? So we can substitute delta S for the surroundings for this term right here. And this is delta S for the system. Anytime we don't have a subscript here, we mean system. So this is going to be the system. And that's equal to, we're going to keep this part. Yep, we're going to keep this part. Delta G over T. And we recognize this as delta S total. Right? Delta S total. So delta S total equals minus delta G over T. So we know that if the system is spontaneous, this has to be positive, right? So if that has to be positive, and there's a negative sign here, then this one needs to be negative, doesn't it? Delta G must be negative in order to give us a positive delta S total. Okay. So if a change in free energy is negative, that means we have a positive delta S total and the reaction is spontaneous. So that's a little easier to deal with because free energy values for various processes are in any reference manual. It's easier to work with that in terms of free energy and temperature to determine whether a process is spontaneous. All right. So let's see. We got, let's see. This is, let's put this one, delta G equals delta H minus T delta S. And also negative delta G over T equals delta S total. There we go. We got those equations that we can work with. So a liquid is vaporized at its boiling point. So we want to predict the sign of each one of these. So a liquid, let's say A, liquid is vaporized at its boiling point. That's the process. Okay. Well, we know that if it's at its boiling point, well, let's take them one at a time. So how about delta? Any work being done? Well, under the right conditions, we can do work because the gas from this, if we confine it, let's do this. If we confine the liquid and then we put a movable piston in here at constant pressure. Okay, now we allow this to move, and if this moves as the gas expands, then we're applying a force against and moving a distance, then we are doing work. Okay. So W, the gas is doing work on the systems, which means what? The sign is negative. In other words, we're doing work on the system, so the work is leaving the system. So that's a negative. Okay. How about Q? Heat is required. We have to add heat to the system. So it's a positive value. We're putting heat into the system, right? Q. We're doing work on the surroundings. How about delta H? Well, if we say this pressure is constant, then the Q is equal to delta H. So delta H would also be positive. Okay. The enthalpy then is positive under those conditions. How about the delta S for the system? Well, let's see. System is in here, and the delta S is increasing for the system. It's more random. So that means we have a positive value. Delta S for the system is positive. How about the surroundings? Well, we're extracting energy from the surroundings, so the energy randomness for the surroundings should be decreasing, right? As heat enters the system, the surroundings become more ordered, so their value is negative. For the surroundings is negative because of that process right there. How about delta G? Okay, delta G. Let's see. If this is delta G for the system, delta G for the system, delta S for total. Well, we don't know that. Oh, duh. At the boiling point, we're at equilibrium. So these two values are equal, add them together, and you get 0. So delta G is 0 at equilibrium. Did that one fly by you?
Yeah.
Okay. Let's see. Okay. At equilibrium, these two values are equal in magnitude and opposite in sign. So the delta S total is 0. Delta S total, if this is 0, then delta S has to be 0, mathematically speaking. Or you can just memorize. Mm-hmm. Delta G is always 0 at phase change. Oh, and if, let's see, is there more to that? No. Delta H equals T delta S. Delta H. Oh, if delta G is 0, then delta H is equal to T times delta S. Right? And these terms don't have subscripts, so they're all system. They're all system related. So at equilibrium, delta H equals T times delta S. Okay, so let's take an example here with numbers. We want to know the delta H of vaporization. How much heat is required to vaporize turn a liquid into a gas? The delta H is equal to 45.7 kilojoules per mole. Its normal boiling point is 72.5 degrees Celsius. We're going to calculate the delta S for the system, delta S for the surroundings, and the delta G for the vaporization of 1 mole of this substance. Okay, we know that at the boiling point, the delta S for the system and the delta S for the surroundings are going to be equal in magnitude and opposite in sign, because the delta S total has to be 0, right? So delta S for this system and the delta S for the surroundings are going to be opposite signs, because the delta S total is equal to 0. So if we find out one of them, then we just change the sign for the other one. Okay, and we know that the delta S for the surroundings is equal to minus delta H over T. So here's a problem where we have to pay close attention to the units of measure, because the standard, the unit of measure in the SI system is joules, not kilojoules, right? So this value needs to be negative 45.7 times 10 to the third joules, because that says kilojoules. This is the kilo part. Okay, divided by the temperature. So we've got 72.5 degrees C plus 273 to make it K. Okay, so this is delta S for the surroundings. Calculator. Let's see. 45.7 exponent 3. Wait a minute. Got to do this first. 45.7, change that sign. Exponent 3. There we go. And then I need 72.5 plus 273. And that's 345.5, right? 0.5 K. Okay. So that divided into the previous value, right? And this is standard notation would be minus 132.3 joules per K. That's the unit of entropy, joules per K. All right, this is surroundings. It's negative. So that's the negative. So the positive is going to be just the opposite, 132.3 joule per K. Okay. Delta G equals 0 because we're at the boiling point. But the entropies can be calculated, right? And there you go. Okay. Oh, Professor Dave wants to talk.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the nonpolar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works, and that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale, but the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. So this particular equation is useful to understand when processes, not just when they're spontaneous with a negative delta G, but under what conditions can we expect them to be spontaneous? And that's in terms of temperature. So if, let's put this up here, delta T, delta H minus T delta S. If delta S happens to be positive and delta H is negative, right? Exothermic reaction would be energetically favorable, and this would be entropically, in other words, the entropy favors it. Then this would be negative, and this would be negative also. This term would be negative. That means this is negative under all conditions. It doesn't matter what the temperature is, it will be favorable. If we go the other direction, if we say this is positive and this is negative, then that makes this positive and this positive. So this is unfavorable under all conditions. If we have, let's see, both positive, right? Then the only way that this can be negative is if this value is bigger than that one, which means temperature has to be high. So this would be favorable at high temperature. Okay. And if the other way around, if this is negative and this is negative, then we want to minimize the size of this one because negative times negative is positive. So this would only be spontaneous at relatively low temperature. And these values depend upon what these values are, because in this case, if this is a very large value, then high temperature means very high. If this is a small value, then high temperature wouldn't have to be as high to give you the negative to offset. So high and low are relative terms. Okay. All right, here comes another difficult concept. I'll do my best. Say we have a gas, a diatomic gas, A2, right? Two A atoms bound together, and it reacts with a diatomic gas B2. And it forms a gas AB at constant temperature. So it'd have to be two of them, wouldn't it? Yeah, to balance it. Okay, the bond energy of AB is greater than either of the reactants. So if the bond energy here between these is much higher than it is here, what does that actually mean? When we say bond energy, actually what we're saying is it takes more energy input to break that bond than it does energy input to break these bonds. Okay, so energy input would have to be enormous here. So where did that energy go? If these bonds are weaker and this one's stronger, then the energy content here is higher than it is here, because now we have to put energy back in to break that bond. So this is an exothermic process. It's a negative delta H for the forward process. That's what that red is on the bottom. So that means that this is lower energy than either of those two. Well, lower energy on this side than on that side. So we would draw it like this, like that. That would be the energy diagram for this reaction. Okay, remember we can calculate the enthalpy of this reaction if we know the energy of the bonds. We did this before, I think, didn't we, last semester? Yeah. We can calculate the enthalpy if we know the bond energies of all the molecules. And we say the bonds broken minus the bonds formed gives us the delta H. Okay, what would be the signs? What would be the signs for each one of these? Well, the delta H, we already determined the delta H is going to be negative. I think that's probably the first one there. Yeah, there we go. Delta H is negative. All right, if we look at the delta S for the system, well, it's probably going to do do them in order. The delta S for the surroundings then would incorporate this value, would be a negative times a negative is a positive divided by the temperature. And that means the delta S for the surroundings would be positive. Okay. How about the system? Well, it's not at equilibrium, so we can't say that the system is just the difference there. So we have to make a big assumption here. If we do say that the delta S for the system is, well, the delta S for the system is going from we're going from 2 moles here, 1 plus 1 is 2, to 2 moles here. So we're going to say that delta S for the system is approximately 0 based upon position. So the delta S total then is going to be positive. And there should be a spontaneous reaction. All right. Okay, there's the third law. And Professor David's talking about it too. this doesn't have a whole lot of meaning for us, except that to say that since the third law of thermodynamics says that the entropy of a perfect crystal at 0K is 0, that is its energy value, that's the only time that that the entropy of any substance is 0. So what that means is that every substance at any temperature has an entropy value. Right? Remember when we were talking about enthalpy earlier, last semester? Enthalpy can be 0. We just set it at 0 for any substance in its most stable form at any element in its most stable form at standard temperature and pressure. We automatically give that one a delta H of 0. So if we had, say, oxygen gas at standard temperature and pressure, then delta H is equal to 0 for that substance, okay, when we do our calculations. But for delta S, every substance has a positive delta S. What we're saying is at absolute 0, it starts at 0. So if the temperature goes beyond 0, then delta S is a value for every substance, even these elements. Right. So you're going to have a delta S value for everything, because we've never gotten to absolute 0. Okay. So similar to our calculations for enthalpy for a reaction, delta S is also a state function. We only need to know the end and the beginning. We don't need to know anything that happens in between. So remember we said that delta H for a reaction is simply the summation of the delta H's for the products minus the sum of the delta H's for the reactants. Okay, and we say the same thing for the delta S. And these are under standard conditions. Right? We'll modify the equation for non-standard conditions later. So we can say the same thing here. We just sum up whatever the delta S's are for the products and subtract the total of the delta S's for the reactants. Okay. So, okay. I'll just read my own statement there. Now, for individual molecules, right, we can talk about, this is for reactions, but we can talk about entropies in terms of individual molecules. Generally speaking, the standard entropy for a molecule increases as the complexity of the molecule increases. So if we use a homologous series, say, let me make room here. Homologous series of hydrocarbons. Right? Our simplest hydrocarbon is hydrocarbon, means hydrogen and carbon. Okay. So if we do the aliphatic series, then we have that is ethane, and then propane, and then butane, and then let's go ahead to pentane. Let's go all the way up to octane. I like octane because I burn it in my gas tank. Here we go. The delta S's for these substances increase. As the molecule becomes more complex. And that makes sense because with this one, you've got two carbons bound together and the hydrogens can spin around. So that gives them some more positions that they can occupy. With this one, you've got three carbons. So you can spin around the bonds. You can also orient them differently like that. And as the number of bonds increases, you have an increasing number of positions that the molecule can occupy. Okay, so in this case, we're going to use water versus hydrogen. So notice that the bonds between the hydrogen and the oxygen, we can have a symmetric stretch. Right? They can both stretch out and in like that, or they can bend this way, or they can do an asymmetric vibration that way, or the molecule can rotate. But if we have diatomic hydrogen, we're not going to show hydrogen. No. Well, if you have hydrogen, what can you do? You can stretch, right? And you can spin. That's about it. Okay. So let's calculate the standard entropy for the following reaction. And notice we've got values for every one of our components. So sodium, we want to take the products first. 2 times sodium hydroxide would be 100, right? 2 times 50. And then 1 hydrogen would be 131. So it'd be 231, right? And then minus the reactants. So 2 times sodium is 102. And 2 times water is 70. Right? Okay. So let's see. 1. That's it. So this is bigger, so that'd be a minus. Minus joules per K. Joules per K. Right? Joules per K mole is the standard entropy because it depends on the number of moles you have of each. But we've already multiplied them times moles, so the moles goes away, and we only have joules per K. So that's the standard entropy for that reaction. Standard conditions. 0, well, let's see, it should be chemical reactions, the standard is 25 degrees Celsius and 1 atmosphere pressure. And if concentrations are involved, which they would be, sodium hydroxide, aqueous solution, it has to be 1 molar. So under those conditions, the standard entropy is minus 11. Okay, how about standard free energy? Well, we have standard free energy values also, and an analogous reaction sequence gives us the values for the delta G. All right, let's see if we can predict these two. A stable diatomic molecule spontaneously forms from its atoms. A stable diatomic spontaneously forms from its atoms. Remember when we were talking about ionization energy? We had to, the molecule or the atom has to be in the gaseous state in order to assess ionization energy, because if it's not, then some of the energy that you're putting in is going to phase change. Right? So it has to be gas. So that's why we're going from a gas here to a gas there, so that we don't introduce any other forms of energy transfer. Okay, so this is what they're talking about there. A stable diatomic molecule spontaneously forms from its atoms. If this is more stable than that, then we have given up energy. Right? It is exothermic. So delta H is negative. Oops. Spontaneous forms means that delta G is also negative. We're saying it's spontaneous, so delta G has to be negative. Well, how about the delta S for the system? We know that the total delta S has to be positive because delta G is negative. But how about for the system? Well, this is going from 2 to 1. It's more ordered, right? So this has to go down, has to be negative. That's why all three of them are negative. Oh, I did put an explanation in there. Sometimes I do and sometimes I don't. All right. Okay, I've got 20 minutes. Let's see how quickly we can get through this one. Well, here we have a problem where phosphorus trichloride plus chlorine gas yields phosphorus pentachloride. And the free energy is negative 92.5 at 25 degrees, which is standard temperature. What will happen to the ratio of partial pressures of PCl5 to partial pressure of PCl3 if the temperature is raised? All right, let's see. Did I work this one out? Or am I going to have to do it? I'm going to have to do it. Okay. Let's see, how many more slides do I have? I don't want to waste time where. Okay, this might be worth working. PCl3 plus Cl2 and PCl5 gas. And we want to know the partial pressures of PCl5 to ratio of PCl5 to PCl3. So the partial pressure ratio of PCl5 to PCl3. What happens to that ratio if the temperature is raised? All right. Let's use Gibbs equation. Delta H minus T delta S. And delta G is a negative. It's a negative value, so we know it's spontaneous going that direction. So what happens if we, and there's some value here, which is, well, we don't know that. So whatever value is here, what happens to the overall? Well, this should be exothermic. We've got 3 bonds there and 2 bonds there, 4 bonds there, and we're forming 5 bonds over here. 1. I'm not sure. I think it's negative, but I'm not positive. Can I solve this problem without knowing that? That's the question. So if we raise the temperature, what's going to happen? It's going to make this term more negative. So it makes it more negative. So raising the temperature makes it more negative, which, and we're starting from standard conditions, but if we raise the temperature, now we're not standard anymore. So if we raise the temperature and make this one more negative, yeah, more negative, then we increase this one and make this one more negative, makes it more spontaneous, which means it's going further that direction. It's going further to the right, which would increase this one and decrease that one. So this ratio should increase. But it says it'll decrease. Okay, how did I get there? Okay. I'm looking at it wrong then. All right. What happens if this is, okay, if we do say that this is negative, then what happens if we increase the temperature? Depends on delta S. Okay, delta S for the system. Delta S for the system is what? It's going from 2 to 1. Delta S is negative. So if we increase this one, this is negative, and we increase this one, it makes it more positive, doesn't it? I can't get an amen? Okay. All right. Let's go back and look at it again. Is this true? Delta S for the system. We've got 1 mole here, 1 mole there, going to 1 mole here. So 2 moles going to 1 means delta S for the system is negative. And this is delta S for the system. All right. So that's negative. And a negative times a negative makes positive. So if we increase the T, it makes it more positive, which decreases this delta G, and it's less spontaneous, so it shifts this direction. Yeah, it shifts to the left, which means this one's going down and this one's going up. So overall, we have a decrease. Okay, so the ratio decreases. Oh, there's my explanation. Delta S is negative, unfavorable. Yes, because the number of moles on either side. Reaction is spontaneous under standard conditions. Delta H must be negative, exothermic, which is favorable, because we've broken these bonds and we formed fewer bonds. It's more stable. Are we telling that in the steps? No, we're not saying that. Well, if it's spontaneous, it does want to go that direction. So that assumption is essentially correct. And then we invoke Le Chatelier when we know which direction the reaction's going. Okay. Now, as if that wasn't enough, what we're trying to do now, we've talked about standard conditions, and we modified the standard conditions for that previous problem. So now we want to be able to quantify those values. If we know the standard free energy, we also know the temperature and the pressure. No, that's not right. Let's focus on the bottom one. What does Q mean? Remember, Q is like the equilibrium constant only it's at non-equilibrium conditions. I'm not sure why that log P is in there. Well, P usually means pressure. Let's stick with Q. I like Q better. And then R is the gas constant, but it has to have the one with the energy term in it. So it's 8.3145 instead of 0.08206. Okay. So what we're trying to do with this diagram is we're approaching our problem in terms of, is there a more stable situation, more stable set of conditions for our system? On the right, we have chemical reactions, and we know chemical reactions tend to settle in the lowest energy possible. And they also have an equilibrium at work. Possibility for equilibrium is at work. And that is represented by the C position for that ball. So we have reactants at A, products at B, and we settle in the middle somewhere where we have a compromise, and that's our equilibrium. But for phase changes, we go straight from A to B. So we're not actually the lowest possible free energy that can be obtained from a system is at equilibrium. Whereas from A to B, that's essentially a completion event. Yeah. All right. So we said that delta G earlier is delta G0 plus RT natural log Q. Okay. And we know if we're at Q, if we're not at equilibrium, then Q tells us which direction the reaction is going to go. But if we are at equilibrium, that means that the actual delta G is 0. Right? So if we're at equilibrium, then we change this term to K. And this is still under standard conditions, but that term is 0. Right? So if we bring this one on the other side and then flip the equation, then delta G0 under equilibrium conditions is minus RT log K. So that's another equation that we can plug in here. And from Q way down here, heat. And then delta G0 equals minus RT log K. So this gives us another way to determine K or to determine delta G. If we already know K at a given temperature, well, if this is delta G0, that has to be 25C. Then we can calculate delta G from our K, or if we know delta G, we can calculate what K would be. All right, I don't know if I want to deal with this one, especially since we don't have much time. Try to extract the concept from these graphs. So what we're looking at is an equilibrium situation where the x-axis is showing us the fraction of A that's reacted. In this reaction, we're going from A to B. Okay, and that's a double barbed arrow. So we've got an equilibrium between A and B. So if we start off with just A and no B, we know it's going to the right. It's going to make more B. until it reaches an equilibrium position where we have A going to B and B going to A. So that's where we stopped in this example. At equilibrium, the fraction of A reacted is 0.75. So we've lost 0.75 of A, and now we have produced B. Well, B comes in from the other direction, and they meet in the middle at that low point. That's where equilibrium occurs, and that's at the lowest possible G. G is on the y-axis, the free energy. So if we write, okay, so that's where P comes in. If these are gases, right now, well, they are gases. We're saying they're gases. So the free energy for A is the free energy under standard conditions for A plus gas constant times Kelvin temperature times natural log of the pressure of A. And the same thing for B. And then that means that the total free energy is whatever is contained in A plus that contained in B. That's where we're at right now. And that's at any position on that graph, that's what G is. So as A disappears, the free energy of, of A decreases since the pressure decreases. And as B appears, the free energy of B increases since the pressure of B is increasing. It's a product. As long as the free energy of G is less than A, the reaction will proceed to the right. And when the free energies are equal to one another, that is, the total is zero, now we're at equilibrium. If that doesn't spin your head around, then you're not normal. You'd have to be a chemistry major to do that. All right, so let's practical applications. So if we have this equation where we have the equilibrium constant, we have a temperature, and we have standard delta G. If under what conditions would delta G, standard delta G be equal to zero? Well, if it's equal to zero, then one of these terms has to be zero. Right? That's the only way it can happen. One of these terms has to be zero. We know that R is not zero. We know temperature is not zero because we're not at absolute zero. So this term must be zero. So under what conditions would natural log of K be equal to zero? Remember? This means that E to the zero equals K. So E to the zero, any number to the zero power is one, right? So that means K must be one. That's just the nature of logarithms. So what we're saying is for delta G0 to be zero, K has to be equal to one. Now, if delta G is less than zero, then this number has to increase to make this negative. So that means K would have to be greater than zero. If we're starting at one at zero, then in order to be greater than zero, then this must also be greater than one. And vice versa. For delta G to be greater than zero, then K would have to be less than zero to make this more positive. That's what we're gleaning from that equation. Okay, I think this is the last concept. Actually, historically speaking, Gibbs and others, they were interested in the maximum amount of work that could be obtained from any physical or chemical process. So that's where the concept of free energy came from. And this is the outcome, or this is the inspiration for the concept of delta G. So the maximum amount of work that can be obtained from any process is equal to this free energy change. And it doesn't have to be standard conditions. Right? Whatever the conditions are that give you this value equal to the maximum amount of work. This is only true, theoretically true for any process, but the actual amount of work that can be obtained from that amount of energy is only true if the processes are reversible. So the very smallest increment of change is required, infinitesimally small, to be reversible. In the real world, all processes are irreversible. So we never realize that amount of work. It's always the actual is always less than the theoretical. There are some losses that are incurred. Okay, temperature dependence of K. So if we start off with this reaction where we're at equilibrium, right, that's what we're saying. If that term, natural log of K, is in that expression, we're at equilibrium, which means that delta G has to be 0. And delta G equals minus RT log K. Here we are, right there. So if we say that delta G 0 equals minus RT log K, that's also equal to delta H 0 minus T delta S 0. Right? So divide the whole equation through by minus RT. And you get, that might be a little hard to follow. Let's see, up to this point, we've got delta G 0 equals minus RT log K equals delta H 0 minus T delta S 0. There we go. If we divide the whole thing through by minus RT, minus RT. So we got minus RT, we got minus RT, and this is minus RT and minus RT. Okay. So this gives us delta G 0 over minus, let's put the minus out here, over RT equals, and this goes out, leaves us with log K equals minus delta H 0 over RT and plus T's cancel delta S 0 over R. Okay. Now, I'm going to factor this out. Minus delta H 0 over R times 1 over T plus delta S 0 over R. Okay. What we're trying to do is to make it look like a straight line formula. This is Y, this is M, slope, this is X, and this is B, y-intercept. Okay. So if we put that in a graph, straight line graph, okay, then we have x-axis is 1 over t, right, which would be k to the minus 1 would be the units, and this would be natural log of the k values. Okay, the slope is going to be negative, right, and the slope is also equal to minus delta H 0 over R, and then the intercept here is equal to delta S 0 over R. So how do we get here? Well, you determine the equilibrium constants at different temperatures, at least 2. 3 or 4 would be better to give you a straight line. And you plot the natural log of your K's at these different temperatures using the inverse of the temperature, and you get this line. And you can extract from that line standard enthalpy, and standard entropy. Okay? There's an example. I think there are one or two problems in the review set that approach this problem. Let's see. I'm going to leave. Let's erase this and leave that equation. That should be part of our group of equations over here. Right. Any real path wastes energy, so we can't get maximum work out of it. All real processes are irreversible. So this is kind of a tongue-in-cheek expression of the laws of thermodynamics. The first law says you can't win because the universe is running down. But you could possibly break even. You can't get more energy out of the system than you put in. Right. Second law says, sorry, you can't break even either because of entropy. Right. Any transfer of energy will result in a waste of energy unless you could couple your reaction to absolute zero. That's the only way that you could break even. Right. We've never been absolute zero, at least not for more than one molecule at a time. There are some research groups that have claimed they reached absolute zero by firing lasers at just the right frequency and energy at an individual molecule to stop it. And they say, all right, no motion, absolute zero. All right, that's not going to do us much good. And then the third law says you can't get out of the game because you can't ever go to absolute zero. Right? So the end result of the first, second, and third law is you're really screwed. Every time we use energy, we degrade its usefulness. So eventually, well, there are various theories about that. The universe is running down, and there are controversies as to whether the universe is eventually going to go out with a whimper, right? Just go cold, or it's going to, the dark matter is going to win, and it's going to recollapse and rebound. Who knows, right? Some people